So first section we're going to look at this week is 5.4, and it's on solving systems of linear equations, but we're going to look at some special cases that can happen. Okay. So when we've done elimination, we've always had one letter cancel out. In a special system, what can happen is both letters would cancel out. So you're left with an equation without any letters. So what happens? So let's think about what can happen graphically, because I think if you think about it visually, that's the easiest way to think about what we've been doing. When we solved this problem, can anybody tell me how many answers did we get for x, and how many different numbers did we get for y? For each one of them, we got how many answers? Yeah, just one. And if we were to draw this on a calculator, and then draw this, or by hand, but a calculator would be faster. If we were to draw these two lines, what would happen at the point -1, 5? Yeah.
They would intersect.
They would intersect. I could draw them quickly and show you, but the idea is if you drew them both, they would cross at -1, 5. So that is one thing that can happen when you draw two lines. They can intersect exactly in one spot, like this. You guys have a picture of that we're going to talk about in a second. That's the normal case. You draw two lines, they make an X shape, and they cross in one spot. But there's two other things that can happen besides making like an X shape. And we'll talk about those on your guided notes. So under the part where it says solutions of systems of linear equations, you want to copy down. A system of linear equations can have one solution, no solution, or infinitely many solutions. This is what we've been doing up until now. Every single problem I've given you has been one solution. And a one solution problem, if you want to visualize what it looks like when you draw it, is your lines look like an X shape. And where they cross is the solution. So you guys have a spot in your guided notes right above the lines that I drew, and you want to fill in what's underlined, one solution. What kind of lines do you think would have no solution if you drew them? Think about the solution is where the lines cross. Yeah? Yeah, when they're parallel. If you draw two lines and they don't ever cross, well, that's a special case. That's a no solution. Because the solution is where they cross and you can't find where they cross. So as a picture, it's easy to see. But what would happen algebraically? What if we're not drawing a picture? What if we're solving it using substitution? What would happen in substitution when there is no solution? That's what we have to figure out. But that's what would happen as a picture. They would never cross. And then the last case is infinitely many. How can two lines cross each other like infinitely many times? Yep.
They were like super small decimals.
I'm not sure. What do you mean?
Like if you were to like go on and on because they were like the numbers kept getting big.
Okay. Lexi? Right, if they were like right on top of each other. I'm not sure if that's what you meant or not. But if the two lines were exactly the same lines and you drew them, well, Where they cross is the solution. And if they cross at every single point because they're right on top of each other, that would be infinitely many solutions. So that's what infinitely many looks like as a graph. But again, the question is, what happens if you're using substitution? How do you know if you're going to get one of these special cases? And that's what we'll look at. So right at the bottom of each graph, you can fill in on your guided notes the explanation of what each one of these is. The lines intersect. In the second case, the lines are parallel. I think somebody used the word parallel. And then in the third case, they're the same line. So we've already focused a lot on one solution. We spent 2 weeks on solving problems that only had one solution. And we did some in the warm-up as well. So I'm not really going to review too many more of those today. Focus today, special cases. That would be either no solution or infinitely many. Does everybody have everything filled in for the diagram of the lines? So how do you know which method to use? Are we going to use elimination? Are we going to use substitution? Or are we going to use graph? We've learned 3 ways to do it. Well, if your equations are set up x, and then a plus or minus, and then a y, and then an equals, and then a number, we're going to use elimination. An example of that would be like 2x plus 3y equals 4. Okay, I'm not really thinking of using substitution there because I don't have a letter by itself. Every letter has a number next to it. So substitution wouldn't be easy with that kind of problem. Okay, so x plus or minus, then a y, then an equals, and then a number. That's elimination. Okay, I'm not going to do this problem. I'm just showing you an example. Now, if it's y equals mx plus b, it could be either substitution or graph. How you're going to know which one it is it's going to depend on what they give you in the problem. If they give you a piece of graph paper in the problem, then they want you to do it with graph. But remember, substitution is just getting a letter by itself. And that's exactly what this is. You have a letter by itself. Well, graphing is also getting a letter by itself. That's why you can do either method. If you see a graph on your problem, like on the test on Edulastic, I give you a blank graph to use, then I want you to solve it with graph. If you don't see a piece of graph paper on your problem, then you can use substitution. Okay, so 1 and 2, you want to put those under where it says what methods to use. Alright, so now we'll go through some problems using the methods we've learned, and I'm going to show you what happens when it's no solution and when it's infinite solutions. Okay, we haven't seen that yet. So this one, well, it's pretty clear what they want you to do. They're giving you graph paper, and they say in the directions, solve by graph. Now, when we graph, keep in mind, we are looking for, we're going to draw 2 lines, and then we're looking for where they what? Yeah? Where they intersect. Yep. Okay. So here's our 2 equations. Let's start with the top one. when you want to graph something, what number do you focus on first? The slope or the y-intercept? Yep, the y-intercept. And where's my y-intercept here? It's at 12. So I'm going to kind of have to estimate because it goes off the graph a little bit. So this goes up to 6, 7, 8, 9. I think it's 10. 6, 7, 8, 9. Yeah, it goes to 10. So 11, I would think would be right about there. And 12, probably right about there. On edge elastic, this wouldn't be a problem because you would have the right size grid you need. So y-intercept is 12. Or what's the other thing we could do? You know what? We could do instead. We could scale the y-axis. That way we're not so far off it. Because even if I do that, I'm still going off my page. What would be a good thing we could scale the y-axis by instead of going by ones? Yeah, twos or what else? I'd go by a certain number here because every number here is divisible by the number I'm thinking of. Yeah, yeah. Let's go by threes. So let's make this 0, 3, 6, 9. Well, that's gonna make it a lot easier because now 12 is on the graph. 15, 18. All right, that's it. So let's put our y-intercept at 12. And now I need to know the slope. What's my slope? Yeah. Yeah, let's think of it as 3 over 1. Because what are the two words that we use when we describe slope? We say the blank over blank. Yeah? Rise over run. The rise is 3. The run is 1. So we need to go up 3 and right 1. I'm at 12. If I go up 3 from 12, what number am I at? Yeah. 15. And I need to go right how many? Yeah. 1. So let's go up to 15 and then right 1. Remember, that really is up 3 because we changed the scale. And then the next one, we have to go up 3 again. So that brings me to 18 and then right 1. I didn't change the scale on the x-axis because I didn't think I needed to. I just left these as... I just left those as ones. And that's okay to do. You can scale one axis and not the other. Okay, so now I can go up 3 again. 18. If I go up 3, brings me to 21, and then right 1. And I can kind of see what's going on. So generally what I do at this point is just continue the pattern. You don't have to do it that many times. It's just because the board is big, it's hard for me to draw a straight line if I don't do that. So I'm going to draw my line. Taking way more points than I needed, but that's my first line. Okay, let's look at the second line. What's my y-intercept of the second line? Yep. Yep, 6. I'm going to put a dot at 6. All right. And I need to think of my slope as a fraction. So, Anaya, how can I make that a fraction?
Over 1.
Yep, put it over 1. So, Caleb, can you describe to me what this slope is saying to do?
It's the slope is 3, negative 3 over 1.
Which means to go
Down.
Down how many?
3.
Down 3 and
To the right 1.
to the right 1. So if we're at 6 and we go down 3, where does that bring me?
What do you mean? So like you're going down 3 and then over 1. So that you...
So like if we're at 6, let's just start with the y-axis. What's down 3 from 6?
Wouldn't be negative 1. I know, 1 over negative 1. Are you looking for the coordinates or what are you looking
Just the number. If you're at 6 and then you move down 3, where does that bring you?
3.
3. So we're going to be down at 3, and then we're going to go right 1. And then if we go down 3 again from 3, we're at 0. And we go right 1. Right? And I think I can already see where the lines are going to cross. That's good enough. So they cross right there. Let me zoom in. And remember that y-axis goes by 3s. So can somebody tell me, where does it look like those two lines cross? Go ahead.
-1, 9.
Yes. So we've gone left 1, and then up 3, 6, 9. So that's not a special case. That's a normal case. You draw two lines, they cross in one spot. It's the kind of problem we did a couple weeks ago. Okay. Any question on that one? All right, let's try example 2. And I think on your guided notes, does it say solve by substitution? Okay, so let's try that. If they're asking us to solve by substitution, it probably means they're going to give us y by itself without a graph. Yes? Yeah. Okay, so let's try this one. Well, let's see what happens. Maybe it'll come out to a special case. Maybe it'll just be a normal case. Okay. Let's see what happens. All right, so we have an equation with y by itself. In fact, both of them have y by itself. Since they both have a letter alone, you're going to take the top one, put parentheses around what comes after the y. And what do I put parentheses around in the bottom? Yep. Around the y. And now, what am I going to do with that 2x minus 3? Yeah. I'm going to put it in. Is that what you said for y?
Yeah.
Yep. So we're going to take that 2x minus 3, and we're going to fill it in for y in the bottom. So let's write that up. So this becomes 2x minus 3. And on the other side is negative 2x minus 7. And we're going to solve. Finn, how would I get all my x's on the same side?
By adding 2x.
Yep. I would add the 2x on both sides. So when you add the 2x on both sides, that's going to cancel it on the right. And on the left, Maya, what do I have now?
You have 4x minus 3.
And on the right?
Negative 7.
Negative 7. Okay. And now we've got the x on the left, so we got to put numbers without x's on the right. How would we move that negative 3 to the right side? Yep, we're going to add the 3. That's gone. Negative 7 plus 3, how much is that going to leave me? Negative 4. And my last step, to get x by itself.
Divide both sides by 4.
Divide both sides by 4. So this seems like a pretty normal problem. We didn't have anything special happen here. That's not a special case. That's just a review of what we've done before. Okay. So we have x equals negative 1. Okay, now as always, we're solving a system. So what letter do we still need to find? 1. So we know x equals negative 1. So take negative 1 and fill it in for x. It does not matter which equation you use. I think the top one is easier just because the number is smaller. So we get y equals 2 times negative 1 minus 3. Okay, and 2 times negative 1 is going to give me how much? Negative 2. And what's negative 2 minus 3?
Minus 3.
Yep, negative 5. Perfect. There you go. So nothing special at all. If we were to draw these two lines on the calculator, they would cross each other at negative 1, negative, what was it, negative 5? Negative 1, negative 5. Any questions on those before we look at now a special case? Okay. Let me now, this is going to be a special case. But first, we want to decide on the method we're going to use. Do we have a letter by itself on one side? Tirza, do we have a letter by itself on one side? No, we don't have a problem like this. Since we don't have a letter by itself, we're not doing substitution, and we're not doing graph. What's the other method we have that we learned and we spent last week on this method? Yeah. Not substitution, because that's when you have a letter by itself. Yeah, we want to use elimination. Ideally, with elimination, if we can add a column up right away and everything cancels, then we're good. Is there a column here that I can add right away and it would cancel out? Thank you. No. There's no column you could add and it would cancel out. So then what we want to do is look at the smaller number and see if we can multiply it by something to make it the opposite of the bigger number without using fractions. Can we multiply 8 by something to get 32? If we can, then we're going to focus on that. Yeah?
4.
Yeah, so yes, we can. Now, ideally, we want this to be a negative 32, and we want this to be a positive 32, so they cancel. So what number would I put in the parentheses? So when I multiply it out, this is a negative 32, and this is a positive 32. Yeah? Perfect, negative 4. So that's like if you were using the template, that's like the number that would be in the box. Let's do this out and see what happens. Lexi, what's negative 4 times 8x? Negative 32x. Abby, what's negative 4 times negative 4y? 16y. Yep. Good. And the last part, might need a calculator a little bit big. What's negative 4 times 20? Anyone think they know? Yep. Negative 8. Yep. And then the bottom equation, we didn't multiply by anything. So copy it over. 32x minus 16y equals 48. And now you're going to see what happens in a special case. let's add these columns up. What's negative 32x plus 32x? Yeah,
They cancel.
they cancel out. That's why we did what we did, because we wanted to cancel the x's. Now add up the next column. Brady, what's 16y and negative 16y?
0.
0. They canceled out. What's on the left-hand side now? I gotta put something there. Yeah? What is it? So what do I put to represent nothing? 0. When everything cancels on one side, you now have a special case. Okay, so we have 0 equals, and we still have to add up what's on the right. Negative 80 plus 48. Negative 32. Okay. At this step, you're done. You have to look at that answer and interpret what that means. This answer says 0 equals negative 32. Does anybody have any thoughts about that? Yeah?
That's incorrect.
That's incorrect. That is not true. That is false. So because we got something that is incorrect, which one of these three cases do you think it is? Yeah?
No solution.
That's a no solution. Okay? If you were to draw these two lines, they would look parallel and they would never cross. But that's what happens when you use elimination and you get no solution. And do I write that down? Okay, let me write down what just happened there. So if you get, just like Aiden said, if you get an incorrect statement, or you get a statement that's not true. So if you get a false statement, the answer is no solution. Now, what do you think the opposite of getting a false statement would be? Yeah? Getting a true statement. A true statement would look something like this. 5 equals 5. Or 0 equals 0. Or something where you have the same number on both sides. These are true statements. So if you get a true statement, let's go back and look at those three cases again and see which one you think it would be. All right. So if you get a true statement, which case do you think happens here? Yeah? Yep. Infinitely many solutions. So if you get a true statement, the answer is infinite solutions. Those are the two things that can happen with a special case. Yeah? Sure. But this one is a no solution because you ended up with a statement that's false. The only way you can end up with a false or a true statement is if all the letters disappear. If all the letters don't disappear, then it's just like the problems we've been doing. You'll get a number for x, and you'll get a number for y. And that's a normal case. But these are the two special things that can happen. There's one. There's two. So make sure you write those two things down. You can just put them under example 3. I'll try to come up with one that's all infinite solutions next. Yep. Yes. Can you wait for Aiden to come in? So any questions here? by, let's see, I think this is under extra practice A. Before you copy it, let me just make sure it's going to work the way I want. Okay, yeah, let's try this one. Extra practice A. Okay, let's see. Do they want me to do graphing in this problem? What's kind of the hint here that it's not graphing? Yep. There's no graph. There's no graph paper. And y isn't by itself. Do you think they want me to do substitution? What would we want to have if we were going to do substitution? Yep. A variable by itself. Do you see a variable by itself? No, there's numbers next to every letter. So we're not going to do substitution. That leaves us with elimination. Start with the first column. Can you multiply this top equation by something? Let's look at the x's. Forget about everything else. Can you multiply -3 by something to make it the opposite of 6? So the goal is, can we get a -6 right here to cancel this +6? If we can, tell me the number that I would have to multiply by to change -3 to the opposite of 6. Yep. 2. So let's put a 2. Don't worry about what's going to happen to everything else. All we're focusing on is getting rid of the x's. If something else disappears at the same time, well, then we'll deal with it. Okay, so not doing anything to the bottom. So copy it over. And let's distribute 2 in the top. Well, Sean, what's 2 times -3x? -6x. Yep. Let's do the next one. What's 2 times 8y? Yeah. 16 y equals, and now 2 times 32. Yeah, 64. Now, add up your columns. Anaya, what's -6x and +6x? 0. Those cancel. Okay, next column. Natalie, what's 16y and -16y? It cancels out. So now, all the letters canceled out, we're looking at a special case. It's either going to be no solution or infinitely many. What's on the left-hand side? Since all the x's and y's canceled, we need to put something. Yep. We're going to put 0. And now, add up the numbers on the right-hand side. One of two things is going to happen. It's either going to come out the same as the number on the left, or it's going to come out different. What's 64 plus -64? Yeah. 0. So we ended up with 0 equals 0. Let's go back here for 1 second. Did we get a false statement? Or did we get a true statement? True. So we got a true statement in this one. This one was false. 0 equals -32. That's not true. 0 equals 0. Yeah, that's true. So when we get a true statement, what do we write down to the answer? Yeah. Yep, there's infinitely many solutions. And remember, if you were to draw these two lines, they would be right on top of each other. They are the exact same line. Okay, so I think we got a good amount of review in there. We did one graphing, one substitution, and then we did both special cases. Okay, so homework tonight, worksheet 5.4. Remember, last week of the term, and we have our last test on Friday.